Okay, I think everyone's here. I don't know who wants to start first.
Well, we can go first.
Okay, today. Hello everyone. My name is Omar Al-Luwaihi, and today me and my teammate Mohammed Al-Maskri and Al-Mu'tasam Al-Abri are going to do our presentation about electrical car. Next. An electrical vehicle is a vehicle which use one or more electrical engines for propulsion, and it gives an energy to the vehicle. And there are a lot of types like car, train, airplane, and so on. And there are classified depending on electrical source. Belong in electrical vehicle are fast and fun and efficient. And the maintenance is simpler and cheaper, and we can like refueling by $1.5 per gallon. Next. And when we are talking about the history of electrical car, as you know, the electrical vehicle was created by the Scotch businessman between 1832 and 1939. But the but with the technical limitation, it couldn't get enough speed, just 32 kilometers per hour. So the electrical car fills and come back with a new look and feature. Next. And electrical vehicle come in different of shapes and size, and also different of super option powered by electricity. And there are two basic electrical car design. As you can see in the first picture, it's all electrical vehicle. It just depends on the electricity. However, in the second picture, it's the plug-in hybrid electrical vehicle, which depend on both both gasoline and electricity. Next slide, please. And as you can see in this slide, we did research about the state in United States, which is Fairmont community. And as you see in this picture, the electrical vehicle are registered in 92% of this state. Also, the number of electrical vehicle increased by 644 vehicle or 17% over the past year. And also about 25% of plug-in vehicle requests in the last quarter were used. Next. And the last point that I am going to talk about is the big data in electrical vehicle. Electrical vehicle makers have found a new ally to make their vehicle gain traction in the market, which is big data. Now, big data is helping automakers and other companies turn this challenge into opportunities. Also, the data will give us a true understanding of electrical vehicle performance. In addition, electrical car produce and store massive amount of data on battery charge rates, location, and tire plus, and so on. And by crossing this big data, automakers can get insight and driver and recharge batteries, and the driver behavior and the battery performance, and all that will help in the rollout of battery vehicle with a longer range. And finally, the large point through is that it show how data can talk the guesswork and battery power taken together. This data give us an overview of how batteries perform in different conditions. That's it.
Okay, so the last time we talked about the electrical cars. We mentioned several things. Some of these things that we mentioned, like what are the companies that produce electrical cars? What are the features of the electrical cars? What part does these electrical cars have? And how do they work? In this presentation, we'll talk more about how the computer in these cars work, what does it do, and how does it do the self-driving, as we know. So as we see in this picture, this computer has like two different chips, and they do different tasks. First of all, let's talk about the auto driving, self-driving for the cars. How does the computer do the self-driving, or what does it need to do the self-driving? We have some steps or some things that go through to do this, to do the self-driving. First of all, the three-dimensional vector. Three-dimensional vector, it's like cameras around the car. So this camera work like a sensor for the car. They take different pictures from around the car, and they try to correct it and transfer it to the computer as signals. The company call it the bird's eye. So it works like an eye for the car. The second thing we have the neural net planner. Neural net planner is a collection of algorithms that take and handle the navigations in the car. So after we take these pictures and we send them to the computer, here the job of the neural net planner come. These algorithms make predictions and simulations and try to do the navigations for the car. The second thing is the improve in the car processing. The improve in the car processing, it needs to be done to the car. It's like a training for the car. Actually, it's not for the car, for the computer. So the producers take the car outside and they put it in different risks. They put it in different situations, different cases. So the car, it's kind of learning from what's going through. So it's can like act when something happens when the user uses the car. So many people are wondering if these electrical cars are safe, and is it safe to like let the car drive itself? Tesla company has approved that or said that the Tesla cars are 10 times safer than the regular cars. And Elon Musk himself said that they have registered one accident while using the autopilot per 4.19 million, and one accident per 2.05 million without the autopilot. So the autopilot is more safer than the other.
Now we will compare electrical cars and petrol cars. First of all, technology. Petrol cars uses IC engines that converts fuels into temperature, energy, and pressure to move the pistons. The force and power produced are never in uniform. It has multiple mechanical balancing issues. and the engine is not self-started. So this makes the energy heavy. On the other hand, electrical cars uses battery packs. With inductor motors, it is quite the opposite of IC engine. They rotate with the help of electromagnetic fields. It is also easy to control the motor speed by adjusting the frequency. Therefore, induction motor is lighter and at the same time it produces more power. Cooling system. The energy produces high amount of waste energy, where inductor motors has less amount of heat energy, or waste heat, I mean. Therefore, the car does not require any source of cooling mechanism. Energy density. The petrol cars has much higher energy density devices. With the energy devices in it, it increases the friction of the tire and the road, which makes turning in corners much more difficult, where electrical cars has a smaller energy density devices installed. This makes turning points of cars are much more easier. Refueling time. Petrol cars have an advantage here. It only takes 5 minutes to fuel a car, but electrical cars take around an hour to charge. The travel cost. Petrol cost has an estimate of $0.1 per mile, while electrical cars has only $0.03 per mile, which makes it one-third cheaper. They have also a lower lifetime maintenance cost compared to petrol cars. They are 50% cheaper. Power. For electrical cars, a single speed transmission is used for the car. Therefore, the speed is easily controlled. It is controlled by the inverter, I mean, simply by just adjusting the output power frequency. They can produce a great torque even at the start, while IC engines struggle at low RPM. However, the control over torque can be controlled instantly, where IC engine has slower response time compared to the inductor engine. This also adds a better traction control for the car. Next slide, please. Now we'll talk about the future of electrical cars. As you can tell, electrical cars are the future. Batteries got a lot better since the introduction of lithium-ion batteries. They have almost 2 times more energy than the normal battery. So the production has increased. This made the manufacture cost even less. The batteries today are good for the longest road trips. On the United States, most road trips are under 100 miles. Next slide, please. For conclusion, electrical cars are just better. They have more torque from the standstill position. They have, since they have lower center mass, they are quieter. Electrical cars are cheaper than gas cars because gas is more expensive, as you can tell from nowadays, and the same distance from charging. You also don't have to get gas. You can just recharge it at home. There is less maintenance, fewer removing parts, no oil change. Electric cars also produce no CO2 at all, so they do not affect the climate change whatsoever. Electrical cars are also leading towards autopilot and self-driven mechanism. This will make the world change its view from to cars from vehicles to transportation as a service. Any questions?
I have a question.
Yeah.
So when it comes to like Tesla smart driving, how do they perform their training sets? Because I imagine they can't do that on like the open road because that's kind of like they don't want to hit someone or something. Do you know that, or did you read that, or not?
They have like specific places for doing the tests. So
Okay.
like they have different tasks and different things. They put it in like different situations, so it kind of know how to react in the real life.
Okay, thank you.
Any other questions?
Well, I guess that's it. Thank you, guys.
All right. I guess who wants, it's either us or the other group at this point. So whoever wants to go, I guess, speak up and start the presentation, I guess.
We can go if you want.
Okay, yeah, we can go. Just want to make sure. Should I share my screen or do one of you guys have it?
Yeah, if you could share yours.
All right, let's start that up. Not from that side.
Okay, so my name's Jasenia Forney. I'm a little sick today, so hopefully my voice lasts long enough. We also have Fred and Dominic for our group. We focus on analog computing and deep learning. If you want to move to the intro. So what is deep learning? It's a subfield of machine learning that is based on artificial neural networks where there are multiple layers of data processing. It imitates how human brains work and how we learn new information. We are reaching a plateau with where we are in the digital world of deep learning because we need more computing power than available. Analog computing is being resurfaced as an answer to these constraints. It combines computation and memory, so it consumes less energy, and it also increases the speed of computations. However, analog does come with its own issues. Some problems we face when using analog computing for deep learning is that it's not as scalable as digital. It's more difficult and time consuming. It is limited to precision by the noise floor. It has more external factors like heat, and there is no easy way to debug the flow of information. In this presentation, we'll be discussing 3 types of analog computing that are being used and researched in the deep learning world. So the first topic we'll be discussing is optics in deep learning. This is the topic that I focused on. So what is analog optical computing? Optical computing is also known as photonic computing. It uses photons produced by lasers or diodes for computation. Conventional computers use electrons while optical uses photons. So why should we use photons instead of electrons? Optical data communication is faster and it uses less power. Optical computing promises to have these same advantages. So conventional computers are based on transistors, which are nonlinear. However, photons are linear. Since deep learning relies on linear algebra, the linearity of optical devices is helpful. When you use a photonic device with analog electronics, you can create multiple accumulate operations as well, which are used in deep learning. And also matrix multiplication can be used. On the next slide. So one example of how matrix multiplication is achieved is using a beam splitter. If you generate 2 light beams with electric field intensities that are proportional to 2 numbers you want to multiply, then you shine the 2 beams into the beam splitter, which combines them and produces two outputs. So an analog multiplier then is used or uses photodetectors to measure the two output beams. So another way that optics is used in deep learning is with fixed weight learning neural networks, which are fast optical neural network learning algorithms. The prototype created is pictured to the right here and is based off an old concept of Stanford matrix multiplier. They did succeed in building a completely analog recurrent neural network with the FWLNNs. However, the results showed that noise limited the precision. So another way optics is used is with analog to digital converters, or ADCs. ADCs have high accuracy quantization and operational stability. However, they have limitations with their bandwidths and high timing jitter. So photonic technologies have helped with these limitations of ADCs, but they can deteriorate the performance of them. So this article talked about how it shows how deep learning technologies are used to increase the power of photonic applications, which introduces us to these deep learning powered photonic ADCs. They are composed of a photonic front end, an electronic quantization, and deep learning data recovery. The photonic front end has a low jitter laser source that provides sampling, optical pulse train, and precise quantization clock. And the deep learning data recovery has two functional neural networks, linearization nets and matching nets. Linearization executes nonlinearity elimination, and matching interleaves data in multiplex channels. In numerical and experimental results, DLP ADC outperforms state-of-the-art commercial and in lab ADCs, and it is compatible with future performance enhancement in terms of accuracy and neural network throughputs. So lastly, we have a spatial optical differentiator where they introduce a neural network in a multi-layered spatial optical differentiator design. The neural network accurately predicted the reflection coefficient after being trained for 30 hours. And it took it about 76 minutes to find the optimum structure from 2,500 trials, which was actually faster compared to general optimization methods. Okay, next slide.
Okay, my name is Dominic, and I'm going to be talking about charge trap transistors, or CTTs, and how they can be used to create some analog neural networks. And first, I'll introduce what exactly are charge trap transistors. They are transistors with a gate that has a high dielectric constant. This gives it the ability to store charge. And this is something we've seen in devices previously, like flash memory, but no one has tried to use flash memory as purely computational devices due to compatibility issues and complexity issues. And so the charge trap transistors in this paper try to combat this by basing their design on already established standardized CMOS processes. And this is in terms of manufacturing techniques and their operating voltages. So it's very compatible with current digital designs. And moving on to how they work, the charge trap transistors can be programmed using voltage pulses at the gate of their transistors. And the figure on the right on the top shows how the charges can be trapped and then detrapped using these pulses. So the top one, that red pulse, is sending positive voltage into the gate through different pulses, and this is charging, or is trapping some charges inside of the transistor. And the green one at the bottom is showing how they can do the same thing with the negative voltage to get rid of the charges inside. And the charge that is trapped inside of these transistors can be stored and then used for computation. And so moving on to how we use these charges is these CTTs can be put into arrays like the bottom right figure. And these arrays can be used for multiplication and accumulation functions. And the weights are stored as the threshold voltages chosen by the pulses we just mentioned. And then at the end, you can see a row of resistors that are used to sum up the drain source currents. And then it turns them into a voltage signal that can then be analyzed. Then why would we use charge trap transistors versus other digital methods? One reason is we know that neural networks rely heavily on matrix multiplication and the multiply accumulate function. And digital implementations of this have to move a lot of data around and waste a lot of power doing so, as the memory has to transport data to and from the CPU for computations. And this CTT array that we are talking about can do this computation locally in the memory, so data doesn't have to be moved around. And they can also be arranged to do all this multiplication in parallel, which greatly increases our throughput. And furthermore, because they base these CTTs on already like standardized CMOS processes, the implementation and compatibility is much better versus other analog alternatives. And so if we go to the next slide, I will show you an example. So they use this array of charge trap transistors to create a neural network that can do handwriting recognition. And on the top left, you can see just a few examples of what I'm talking about. And below it is the process it goes through to analyze each digit. So first, in the digital domain, the values of the neuron weights are loaded into a pulse generator, which we just talked about in the previous slide. And then these pulses are sent out to charge the charge trap transistors to the desired value. And these stored charges are the weights of our neurons. And then the calibration data and image data of the handwritten digits are added to the circuit. And then the network will compute and measure outputs and then feed them to an analog to digital converter. And once it's done converting, the digital data or the analog data is now in digital bits that are accumulated sequentially, and then fed into a calibration algorithm, and the results are then stored. The results are shown on the top right, and we can see that when the network had at least one or more hidden layer, the accuracy of the model was in the high 90s. And we can see that it needed a resolution of at least 8 bits to get this high accuracy. And they also compared this 8-bit accuracy to a 32-bit accuracy, and it was within 2%. So with only having a resolution of 8 bits, we're able to save a lot of hardware and power with only sacrificing 2% of accuracy. Then in the bottom right, we compare this arrangement to other digital-based ones. And we can see that they have the same 28 nanometer process using CMOS. And then the CTT charge trap engine had a much smaller area. It used much less power, ran similar clock speeds, and did over 76,000 more multiply accumulate functions over the same clock cycle. And that's it.
Okay, hello everyone. My name is Fred Quispe, and we will now be discussing some designs of neural network circuits. As we mentioned earlier, analog provides a greater advantage over digital computing when it comes to response time and power consumption. While there are challenges to this approach, there is a substantial commercial value in designing and implementing neural networks into hardware. Now, when designing a neural network into hardware, some goals that many strive for is the simplicity of the design, as well as the simplicity of training the data, training the network, and reconfigurability. Now, reconfigurability is extremely important in order to be able to change weights in a neural network, as well as be able to provide a framework for other cases that can be used in the future. So current neural network circuits are based off of memristor-based designs, where the resistance of the device are able to be programmed and stored. And this is actually a good selection because it has good compatibility with CMOS, current CMOS technology. It has a small device area for on-chip, and it's non-volatile. It has really fast speeds, and it, as we talked about before, it dissipates very, very low power when compared to digital computing, and it's very scalable as well. Some other ones, analog vector matrix multipliers, they actually offer more benefits of power and performance when they're compared to the digital implementation version. And another technique that's been proposed that's to be realized is a back propagation algorithm. And those are actually being used into different learning architectures and being implemented into hardware as well. So we're going to examine a case, mostly a paper where a neural network was designed into hardware. And it was actually done, this was actually done to be able to test RF devices to check whether they are working as intended or not. So current testing methods actually require sophisticated testing equipment to test whether the device is good or bad. Let's see. And they actually require equipment that is built off of the circuit. So this requires the RF signals to be translated or converted to DC signals in order to test. In this paper, the goal was to implement a classifier algorithm into hardware that would be built into the device or near the device in question. And this way, the analog signals can be used as the inputs to the algorithm without having to convert to a digital format. Now, they actually accomplished this by designing a standard 2-layer neural network that we're all kind of familiar with and using a nonlinear sigmoid activation function. Now, the interesting part is the circuit design. On the right-hand side, you'll see a circuit that models a synapse unit. This is where the multiplication function comes into play. And in this case, the voltage input is provided to these two transistors, and it multiplies this current that's provided by this bottom group of transistors on the bottom. This bottom circuit this bottom transistors actually represent the weight that's going to be multiplied. So the final, let's see, the final results that the paper showed was that the training error was better for software implementation, but the validation error was slightly better for hardware. So the overall goal of the paper was basically to make the case that the analog implementation was comparable to a digital, and they were able to accomplish this goal. In doing so, they provided a good base for others to kind of expand on that topic and improve that analog design. So in conclusion, we presented 3 methods of analog computing and their applications to deep learning. Jasenia talked about optics. Dominic talked about charge trap transistors, and I talked about a specific case study with RF devices. We presented reasons why we should turn to analog computing rather than rely more on digital computing. And those reasons were they use less power and they are more efficient with the area that they take up on chips. They're also able to do parallel computing at a better speed and a better, I guess it has better efficiency in that way. Finally, analog can be used alongside digital methods to create efficient, balanced computing engines. And these are our references we used for the paper. Are there any questions? Okay, if there are no questions, I think we're done with the presentation and we can move on.
Okay. So we're the Big Data and Smart Grids group. And the team is composed of me, Adriana Gustoni, Kimberly Follenkamp, and Mohamed Al Ghafri. And we're going to start by just recapping the problem that we were talking about in the first in our first meeting, which is big data analytics and the smart grid, and looking at security risks and certain solutions, looking specifically into our data sources, prediction modeling, and the applications of these models and different security risks and solutions. Our final goal is to understand big data management and get an insight on security and understand how these can be used in smart grid. So I'm going to pass it to Mohamed, and he's going to talk about the data sources.
Hello everyone. I am Mohamed Al Ghafri, and I'm going to talk about two sections in our paper. The first one is the sources of data in smart grid. So there are multiple sources of data in smart grid, such as sensors, grid devices, detectors, smart meters, and customer device. These data are some of them big data and are not from the same source. So they have different type of data, and the measurements of these data are different. So here is an example of sources. The first one is a digital fault recorder, and it's a device which is used to record if there is any fault or disturbance could happen, and the quantity being measured there is a load variation, transient phase angle changes, and power disturbance. The next one is sensors, and there is a massive implementation of sensors in the smart grid, and these sensors are used to measure like frequency, voltage, the power, energy, and even weather and temperature. The next source is SCADA, and SCADA is it's a system used to monitor and control events in smart grid, and simply it's a data acquisition. The next source is a phasor measurement unit. It's a device for time synchronized measurements with phase angles. So it's used to measure voltage and current by phase and magnitude. And here is in the figure other sources for the data in smart grid and the quantity being measured. Next slide. Next slide is the data structures. So the collected data from the sources will belong to one of the following structure. Structured data, which is the data that has a known structure and format, and it could be selectable. For example, load control, marketing system, dispatching automation, and distribution management. The next type is semi-structured data, and it's like the data related to a text. So the pattern of the data could be seen, and for example, we have web surface data, and the next one is unstructured data, which is a type of the data that is not defined. And for example, we have customer surface, and also there are some some data in smart grid that can be both structured data, semi-structured, or unstructured data. Can be like a mix of all of the three. Next slide. So the next section is we focus on a software and applications inspired by big data. So we study like the software power system simulator for engineering, PSSE, and we mention the challenges, the problem and how it's solved, and then the challenges, how it could be solved by the software, how it can be processed the big data. So let's consider a system with any number of the buses, and the goal is to do a power flow analysis, which is a computation of voltage and current at all buses, and we determine the real and reactive power flow in the system. These are the equations. However, these equations are non-linear equations due to the cosine sign and the product of the voltage. So the method is used to solve the above equation is Newton-Raphson solution, which is it's an iterative method, finding the roots by iteration, and demand a series of successive approximation. There are 3 steps. First one, you guess, and then you check, and then you update, and then you're gonna repeat that for each bus. So it's gonna be like, it does work, but it does work for, you can solve it by hand for a small number of buses. But if we have large number of buses, it's gonna be really hard and it's gonna take a long time because it's gonna process a big data. So and then we're gonna have the software, which is the power system simulator for engineering. It's a powerful software used in a power industry to analyze the transmission, planning, and operation. And also is used for for example, the power flow, dynamics, and transient stability simulation, and much more. Next slide. So here is an example of 21 buses, and we would like to do a power flow analysis. Indeed, it does take like 11 iterations to solve it by the Newton-Raphson. However, we can do it in the software by just only import the data, and we can simply do the power flow analysis. And here's the link for the software, how it does work. Does the sound work? Or? So here's take like 11 iteration to do it. So if we're gonna do it by hand, it's gonna be, takes a long time, but by the software, it's so simple. Just we do the Newton-Raphson, and then we click the report to have the report, which is gonna show us the power flow analysis in each bus for the 21 bus we have. So here's, we click the bus report, and it's gonna be, we're gonna show the report for each bus. That's the report. And here is the report for each bus with the power flow and everything on it. You can move to the slide, to the next one. And for the next one, here is like the software and the applications and the software created for them, and the creator for them, the name of the creator, which is empowered by a big data and inspired and empowered by a big data. Thank you.
All right, my name is Adriano Gusoni, and I'm going to be talking about the predictive modeling, specifically the use cases for these. The first use case that we can go over for predictive modeling is energy demand forecasting, which is a overall demand forecasting. So we already know that depending on things like time and temperature, or time of the year and time of the day, we can expect different demands to occur, and we can get better and better models for these different forecasts based on our data that we can collect. We can do energy consumption prediction, which is different from demand in the sense that we specifically have to take into account areas and certain locations of high or low consumption. So it's similar to demand, but we need to take into account position and location as well as the energy demands from these places. We can also do things like renewable energy parameters tracking. So we can get information on wind, weather, humidity, temperature, wind speed, or rainfall. And we can make models that, or rather we already have models that can give us an estimate on weather patterns basically, and we can predict how much power we can be getting from specific renewable energy farms, which will let us do the last point, which is short-term load forecasting. And short-term load forecasting is similar to demand forecasting, but it is much more granular and short-term. Basically, it's in a smaller temporal range than energy demand forecasting. The predictive models that we can use for these different use cases fall into one of two categories, which are either machine learning methods like neural networks to support vector machines, or recursive partitioning. And the main ones focused on by the paper, or one of the papers that we went through, was neural networks. Obviously, we've been through this in class. Artificial neural networks or deep neural networks. They have one input, one output, and depending on which type it is, we get a number of hidden layers, which is where most of the computation comes in. We have input weights, and the best part about neural networks is that we can use nonlinear functions as well for we can use nonlinear functions to get our predictive models. This is important because our meteorological data is generally going to be nonlinear. And we can use different metrics like the mean absolute error or root mean square error, or symmetrical mean average percentage error to find our evaluation metrics and fine tune the accuracy of these neural networks. Then we can look at recursive partitioning, which is a different method that uses decision trees. These are normally called recursive partitioning and regression trees. So it's our part. These fall under classification and regression trees, which regression trees are a continuous form of classification. What that means is that we can use these for energy consumption, which is a continuous output, as we're always going to be needing, or there's always going to be energy consumption. The algorithm builds the decision tree, like we can see on the right. It builds a decision tree based on different inputs at different nodes, and these nodes are chosen based on points of highest reduction of impurity. And they split based on lower and higher values. And the further down we go, we can find different different responses from the prediction. These responses are then averaged out, and they are later pruned, meaning that the decision trees with the best average response are going to be the ones that are focused on more heavily. And they use a cross-validation procedure for the pruning of the trees. And finally, they're all evaluated using a Gini index or a Gini formula, which is similar to a logarithmic formula, basically. Finally, the random forest, which is similar to the regression tree. It is a tree partitioning method that makes several decision trees. It's similar to the regression tree in the sense that it makes the trees, but the random forest makes multiple of them. And the different data is separated randomly into different candidate variables. We get the same average response out of the trees, and we find the best trees, basically the best branches in each tree to get our final response. We use an average for those as well. And it uses the analysis of variance, or ANOVA statistical method, for evaluation on those. And I will pass it on to Kimberly.
Hi, I'm Kimberly Fullenkamp. Here are some techniques and platforms that are used in big data management for smart grids. First, we have the cloud architecture, which is with the new up and coming clouds being used more and more for data. It's important to be analyzed. So an interesting thing is when compared to a non-cloud system, cloud system is slower, it has slower execution time, but it's more consistent and more efficient, which is pretty important. Next, we have the Hadoop MapReduce. It's better for analysis of more empirical static data, and it's very promising due to like scalability, fault tolerance, automatic failure restoration techniques, and stuff like that. There's also something called I2 MapReduce. It's a more advanced version of MapReduce, more tailored to power systems because it's a little bit more iterative, a little bit more better and smarter for those kinds of activities. Next, we have Apache Spark. It's better for analysis for real-time systems and stream data, which we learned about in class. It has very fast detection of any kind of faults or any kind of events that occur in a power system or in a smart grid. Next, we have general analytics of data mining. Basically, data mining is not something new in the power system, but it used to be a more SQL-based system, and now they're trying to push it more towards machine learning and things like that. Next slide. So here are some applied real solutions that these companies have put out. First, we have Accenture, I think it's pronounced. They have the Intelligent Network Data Enterprise. Basically, it's this Irish-based IT consulting company. They put out this architecture, which has a lot of basically its own platform, its own algorithm to deal with all this big data. It has a lot of new technology to sort of interface with smart meters and PMUs and things like that that were discussed earlier. Next, we have Iberdrola's digital transformation program. Basically, it's the Spanish company that this one has not been implemented yet because I looked at their newsletter. It was supposed to be implemented in about 2019 to 2021, and it's 2021 now, and it's not quite implemented yet, but it definitely looks like they're pushing for it. And basically, it's just this big data management system. Next slide. So here are some other applications. We have the wide area situational awareness system. It's basically more advanced of the SCADA systems, which are supervisory control and data acquisition. It just provides more accurate information and more monitoring capabilities. Next, we have event identification and prevention maintenance. So basically, it's fault management. Anytime there's a fault in a system, it's able to detect it and let dispatchers know when to send people out or when to shut down that part of the system so it doesn't harm any equipment. Next, we have big data driven demand response. Demand response is basically when the consumer adjusts their power consumption based on how much supply the utility provides. And next we have system security and theft prevention. Obviously, this is very important and pretty easy to figure out, as if there's any kind of change with all the big data they find, they'll be able to tell. There's not as much of the security implementations in place yet for big data specifically, but they're definitely working towards that. Next slide. So as a conclusion, basically, as the smart grid gets bigger, it's very important to keep in mind where all this new data is coming from and how it's going to be analyzed. And collected data isn't always helpful, and certain models kind of help us interpret that a little bit better. Next slide. We have our responsibilities. Next, we have references, and then next slide is just questions.
I had a question with the video that was shown. What was the software again that you were using? I thought it was really cool that you had that in there.
It's a PSSE, the power system software for power system simulator for engineering. It's used in a power flow, transient stability simulation also, and for dynamics. It's used for different things. It's developed by Siemens, the company,
Mhm.
and
Okay.
it's for the power flow.
Yeah, that's cool.
Guess that's it.
All right. Yep. I guess that's the end of all our presentations. Good job, everyone. And that's it. Yeah. Thanks, everyone.
Thanks, guys.
Goodbye.
Thanks.